Okay, 11, let's get started. The sound is still good, Manuel? Sound is good? Okay, hello everyone. Thank you for joining this webinar on Smart Grid. My name is Henry, and so today I will demonstrate how you can use emtp for the study of microgrid and smart grid. Okay, before we start, for the one of you that are not familiar with WebEx, if you go at the top of your screen, a small, or actually on the side of your screen as well, you should have an chat option, so you can ask us questions during the webinar. From time to time, I will ask you some questions so you can answer through the chat. One thing, when you use this chat, please select to send the message to all panelists, because if you send it to me, I will not be able to answer while I'm speaking. So please send it to all panelists. Okay, so also before all, so two things actually I'm not. Okay, and this webinar will not be about that. I am not a utility manager, so I will not tell you how smart grid are the future. I guess if you're here today, you know that already. And I will not through some general concept about microgrid. We all agree they are very important at a certain stage, but here it's not the goal of this webinar. Second thing, I'm not a professor from a university, or I'm not a PhD student, so I'm not here to show you a new technique for islanding detection or microgrid. No, I'm an emtp engineer, and so the purpose of this webinar is to show how emtp can help you with the study of microgrid, to do simulation of microgrid under balanced and unbalanced condition, to study and to develop some islanding detection strategy, to study the stability and the performance of the controllers in islanded and connected mode, also how to monitor the power quality generated by the inverters, well, which is affected by the converters, and finally, well, in every other subject actually. Okay, so here is the content of today. So first we will look a little bit how in emtp we can model the VSC-based DGs, so the average value model. Then we'll compare average value model with detail model. We'll look at the different control strategy, the PQ, the PV, the VF for islanding mode. So we'll look at all of that. Then we'll have a quick look at the battery energy storage system. Okay, and see like the different type of battery, the DC-DC converter, etc. Then we'll go through the islanding detection. Okay, so we'll see, actually most of you probably know that already. It exists several methods to detect islanding. They can be passive, where you simply look at some signals of the network, like the frequency, the voltage, and you have to guess if you are islanded or not. Or you have some active method where actually the DG injects some signals to see if something changed. And we'll look at one example of those islanding detection, which is the negative sequence current injection. Okay, then we'll see how the battery, for example, or other equipment like STATCOM or SVC can be used for VAR compensation to maintain the voltage of a microgrid in the connected mode, but also, of course, in islanded mode. Okay, then quickly, okay, I won't have enough time to talk about PMUs today, but we will see how we can use several PMU in one microgrid to have a more precise image of the frequency and the voltage. And so finally, just for fun, we'll do a small black start of a network. So we'll start from a network like completely shut off, and slowly we'll energize everything. We'll start some diesel generator and synchronize the load. Okay, so I hope you will enjoy this content. That's the one I have for you today. Okay, so before all, to study those microgrid, we actually developed a small library that we put on the Exchange platform. So it's completely free. I will download it now and install it now so that you can see how to do. So you go on our website, okay, and you go to the section support exchange platform, and you can see it here. Okay, I just put it today. So it's the Microgrid library. You can download that. Okay, you can do it after the webinar. Okay, so you let it download. Inside there is an executive file, and you just have to install this executive file. Okay, so let me unzip it. Okay, and you just start the executive file. Then here you select wherever your emtp is installed. Okay, in my case I will use today the user version. And you install it. Okay, so it's pretty fast. And so now you see that when you start the emtp, and you create a new blank case, okay, now you have a new library in a microgrid with a lot of very useful things inside, like three-phase inverters. You actually have the inverters themselves with only the IGBTs inside, some battery, some low-pass filter, delays, okay, everything that are useful for to study microgrids. You also have some wind parks and photovoltaic parks. Okay, so let's get started now with the study itself. So the first thing we will do together is build like that a very small network that can be very useful to test islandic detection or DGs control. Okay, so it's based on the standard UL 1741. Okay, and it's a very particular network. Why is it particular? Because the value of RLC are chosen so that first the power of the load match directly the generation of the DG. So in the end, in this configuration, no power is from the grid. Okay. Secondly, the RLC value are calculated so that the natural frequency of this load is 60 Hertz. And so then why it's so challenging? Because as soon as the switch open, first, since the grid doesn't produce any power, since no power is from the grid, we barely cut any current. And since also the natural frequency of this load is 60 Hertz, even if we create like that a disturbance, there is no difference in the frequency. So it's completely invisible from the DG to see an event like that. And so we can guess that all the passive method will not be able to see the islanding in that case, but the active method will be able to. Okay, so we will do that together. The goal also is to teach you how to learn emtp. So I will build this network live right now, and so that you can learn as well. Okay, so I just opened a new blank case in emtp. So first I have to save it. Okay, you know that. So I will save it. I will create a new folder in my desktop named Microgrid. Okay, so let's start. So from this library, I will bring the inverter. Oh, okay. Apparently I had some trouble with the sound. I guess it's better now. I will try to, I have to hold my microphone. Okay, so here I have the three-phase inverter. Okay, so I will connect this inverter to a DC source, so it can be a battery or whatever. So for now, let's take a simple DC source. Okay, the voltage of this DC source will be 2 kilovolts. Okay, so here we have our DC source. Here we have the AC grid. We have to ground this. We have to ground the DC source, okay, to avoid floating network. But here, what we'll do is ground it with a high impedance or actually a very small capacitance, so that it's actually floating. Okay, so I use a very small capacitance and I ground it. Okay, so then the inverter itself. Okay, so in the first tab we'll put the power of it. It will be 2.5 The rated voltage of the grid will be 13.8. Okay, the DC voltage, as we said, it's 2. And also here we will initialize our DG with the load flow. You have two options really. You can choose no initialization. In that case, you will study the startup, okay, of the DG, or you can choose to initialize your DG with the load flow. In that case, the DG will be initialized during the load flow simulation, and when you start the time domain simulation, you have the same power generated during the load flow. I will come back a little bit later on the load flow in emtp, but just to let you know, emtp is a transient software, but we can do time domain simulation as well as load flow, which you will see can be very convenient in case of microgrid where you have a lot of different load power source. Okay, so in the load flow here I have a power reference. As you see, it's from AC to DC, so I have to put -1 if I want to go from DC to AC. Okay, then you enter the value of the reactance of the transformer. So if I have to do a parallel with here, okay, that's the value of the reactor here and the transformer. So I will lump them together. Okay, so the nominal power is 2.5. The grid side is 13.8. Okay, the converter side is 0.6. Okay, and the resistance is 1%. And the reactance is this guy. Okay, so that's for the, here we have together the reactor and the transformer. You can select if you want to have only a reactor and put if you don't have a step-up transformer, so it's an option of this model. Then in the inverter data, for now we'll use the average model. I will discuss after the difference between average model and detail model. So as you probably know, those kind of DGs, they work with inverters which are driving by PWM. Okay, so here it's the frequency of the PWM. Again, I will come back on that later. In the end, if you use the average model, average value model, this information is not very useful because you have no PWM for the average model. But for the detail model, you do. Here you also have the option to tune a RLC filter. In our case, we have none of them, so I just put very big value so that this thing doesn't exist. Okay, and a very small capacitance. Okay, and finally, for the control data. So for the control data, you have different options. Okay, you can, if you want, set up, for example, if you want to monitor only the power, so you select to control the power here, and you put the reference of power and the time constant of the controller. Same thing here, if you control the voltage or the reactive power. So same thing, you put the reference and the frequency, the time response of the controller. You can also control the DC voltage. You can use a droop control that monitor both the power and the DC voltage. You can select to control the grid voltage and the frequency. So it's typically the type of control we'll use in islanding mode. Okay, when we have no network to give a frequency and angle reference for the grid, then one of the DG has to become the slack. Okay, so you determine the voltage and the frequency. And finally, you have the option as well to have all these choice from a bundle as we see here. Okay, so one of the input of this bundle will be the type of control. So 1, 2, 3, 4. 1 for power, 2 for DC, 3 for droop, and 4 for VACF. And then an input for each reference. Okay, so let's enter here quickly the value. So as we said here, it was 0.75 approximately. Same thing here. So that's the impedance at to the point of common connection. Okay, actually, at first we'll only control the power. Okay, so -1, and the reactive power will be 0. Okay. So now we're ready to go. So then I just have to build the rest of the network. Okay, so what do? I add first a power meter. Okay, so I monitor the power going out of the inverter. Then here we'll add a switch. Okay, the switch will be closed all the time. We'll just use it actually to display the power in load flow. Okay, and so finally we'll draw like that. We'll build like that the local load. Okay, so I bring an inductance, a capacitance, and a resistance. Okay, we connect them all to the ground. And the value of those, so remember the value, they are chosen so that the natural frequency of this load is 6 Hz. Okay, and that the power consumption and reactive power match directly the DG generation. And so in the end, no power is from the grid. Okay, so here, that's the value of the resistance. Here, that's the value of the inductance. And finally, the capacitance. Here we go. And then we connect the rest of the grid. Okay, do we have... okay. 1 second, apparently we have trouble with the sound, so let me try to improve that. You know what?
I think it's good like that.
It's good like that, okay. Well, let me know if it is. It's not very comfortable, but we'll do it like that. Okay, is it better now? Whoever was complaining, yeah, it's good? Okay, sorry about that. Okay, so let's finish that. So I had now a second switch to monitor the power from the grid, and I add the grid. So the grid, you can find that in the source, in the library source, and you know the equivalent of a grid, it's voltage plus impedance, Tevna equivalent. So you can find it here. Still not good? Okay, wait. Let's see. Is any microphone? How is it now? Is it better? The same?
I think the quality is less good, but at least it's constant, so it's better.
Well, okay, so let's do it like that. I will try to get my computer closer. Okay, and I speak louder as well. Okay, so now I had the rest of the grid. Okay, so it's a 13.8, and actually the impedance of this grid, it's 10 millihenry. Okay, so now our network is set. So we'll run the load flow of that. So here it's a very simple load flow. Okay, we have here a slack and a DG. So no surprise, but it's just to verify. Okay, so for the one of you that don't know how to run a load flow in the emtp, it's pretty easy. So for the slack, you have to connect to it a load flow bus. Okay, you can find that in the library source, and you can drag and drop the load flow bus. So as you know, a slack gives the reference for the voltage and the angle. Okay, and you go and link this slack with the source, which name is VWZ1. Okay, now they are linked together. And you do the same thing in the source. Okay, from the DG point of view, there is nothing to do. Then, to be able to display the result of the load flow, okay, you have to go to the library options and drag and drop the view steady state. Okay, and so here in this device you have some different options. So one important is like to put the base of the power. Okay, so now we are all ready to go. We just have to choose where we want to display the power. So we set inside the switch. So we right click on the switch, go to steady state view and select the power and reactive power. Okay, so I'm good to go. Let me double check quickly all the parameters enter in here to make sure I haven't done big mistakes. I mean, we'll see it very fast if I did, but if we can avoid that. Oh, here's one. I have to put 0 here. What is that? So that is to actually, it's 2 parameters to do the droop control in the VF mode, in islanding mode, when you have several DGs on the same microgrid. We'll see that later, but for now I put them 0, so I control directly the voltage and the frequency. Okay, I think all the rest is fine. Okay, so let's run the load flow simulation to see if everything is going well. So we go to simulate, simulation options, and we select find load flow. And we run that. Okay, so as we see here, now I have all the power generated by the DG, so it's 2.5. Okay, and here it's not normal. I should have 0 in the reactive power. Oh, and the problem is because I didn't input the good value here. It's 62. So good thing actually we had the load flow in that case. We can see quickly that something went wrong. Here we go now. As you see, no power is from the grid, and everything is from the DG. Okay, so I repeat again, it's the worst condition to detect islanding. Okay, so let's run now the time domain simulation. Even if nothing happened here, we can still look at the waveform in time domain. So for that, okay, as you know, you have to add some meters. Okay, so let's add some meters. So like 1 voltage meter here, for example. So we can call that VDG. We have already a meter here, the power meter. Let's call it PQDG. What else? Let's put a positive sequence meter. Okay, so I use here in the meter the 0, 1, 2 sequences voltage. And I want to monitor the positive sequence here. C1. Okay, and finally, actually we can also monitor the frequency. Okay, so how do we do that? First we use a voltage here, function of the time, which is like this VT. What do they do? It measures the voltage here and give an output in control. Okay, and so then here I can put a frequency meter, which is here in the library, control signal meter. So what I do is I monitor the frequency on phase B, but the network is balanced, so it will be the same frequency in all phases. Okay, so how does it work, this frequency meter? It's very simply a 0 crossing. Okay, so we just check out the 0 crossing of the voltage to determine the frequency. And you can put a range like that to avoid, you know, when you have high frequency, you can have multiple crossing, so to filter that. So it's not a super efficient way, but I mean, for this case it works. Okay, later on we'll see a better way with like PLL to monitor the frequency properly. Okay, and I put the scope for that. Okay, so let's run the time domain simulation here. Let me check if I didn't forget anything. I think we are good to go. Yeah, so let's go. Okay, so I uncheck find load flow simulation, and this time I select find the steady state solution. We initialize the simulation with the result of the load flow, and we find the time domain simulation. So anytime I run, that's everything that emtp does. Okay, so the time step. So for now, we are using an average value model for the DG. So we don't have much limitation on the time step. Typical value for this kind of application is 50 microsecond. Okay, and we can simulate that for 1 second. Okay, so you will see that maybe if you use other software for this kind of application, often it's very slow to simulate. Okay, but you'll see in that case it's actually very fast. Okay, so I run the case, and so you see it took like 1 second to simulate 1 second. Usually it's faster, but now I'm using WebEx. I'm also recording the session, so all that takes some power from my computer, but it's still pretty fast. Okay, so let's look at the results of that. So here nothing happened. Okay, so we are going to look the result in steady state. So to look at the results, I went a little bit fast on that. You click on View Scopes with Scope View, and you will have available all the scope that are here. So as you see in Scope View, you have 2 windows. So the first one, Control Scope, you have the Power Scope, the V1, and the FREC. So let's look at them. So we click once of them, and they come here in the selected signal. Then let's look at the node voltage. So in the signal type, I select node voltage, and I plot them as well. Okay, actually let's put them on another page so that it's more clear. Okay, so as expected, okay, nothing happened. We're in steady state, but I mean it's pretty good. The model works. We see the voltage is constant, and we can see the power. So at the beginning, we start the power meter. As you know, they take 1 cycle to identify the real power. So the first 20 milliseconds really, or 16 milliseconds really are not to be considered. But you see after we have the good power and 0 for the reactive power. Here we have a small transient. Okay, I will discuss that right after. It's for the way we initialize the DG. Okay, so at point 1 we initialize the DG, so we have a small transient, but quickly we reach the new steady state. And so here it's really the control that matter, and you see that the control works. We have 2.5 exponent 6 for the power and 0 for the reactive power, and everything looks good in that case. Okay, so let's visit a little bit this DG, okay, this inverter. So for the initialization, okay, that's where is this information. So let's see what is that. How do we work initialization? Well, what's the problem with initialization? The problem is that this an inverter has no frequency model. Okay, the opening and closing of the gate of the IGBTs depend on the control, so it has no frequency model. So to do the load flow and the steady state, we need a frequency model. So what we do is that for that, we have this box which decouple the rest of the DG with the grid only for the initialization. For the load flow, this will take the form of a load flow bus, and it will inject the power and the reactive power the DG is supposed to inject. So no problem for the load flow. The load flow will always converge thanks to that and make sense. Then when we start the time domain simulation, for the first 0.1 second, we have an ideal voltage source here that maintains the condition of the load flow. The time for the rest of for the control and the IGBTs to reach the same condition. When it's done, we disconnect the ideal voltage source and we connect the inverter. So that's what happened here. Okay, as you see, we have a little transient, but it's really not a problem. Okay, and it's actually a very efficient way to do that. So then what do we have? Okay, we have the step-up transformer here with the reactor and they are lumped together. We have the filter here that we disable. And here we have the average value model of inverter. I will come back on this guy after. So the control now. Okay, so that's the interesting part. Here, this inverter is a DQ0 control. Okay, so as you know, DQ0 it's a very, very good way to do control, especially in balanced condition. In unbalanced condition, you can see a second harmonic in the DQ0 signals, so it can be a good idea to filter that, or to use another type of filter, another type of control. Okay, so you see the measurement here from the voltage, the current, everywhere on our DG. And if we go inside, okay, so that's the control. First, we convert everything into PU. So here we are really like in the control side, okay? So we are not talking about power anymore. It's really control, so it will be filters, transfer function. So you can build all that with the MTP. Okay, so here you convert to PU, so it's only gain, okay? Then you have the low pass filter, which cut the high frequencies. We have here a little bit about protection, but we didn't enable the protection in that case. Okay, we have some overcurrent protection, but it's disabled for now. And that's what that is interesting for us, the control. Okay, I won't get too much into detail right now. Okay, I will get much more in detail while the webinar goes through. But what do we do? Okay, here we have the DQ0 transformation. First, we have a Clark transformation and a DQ0 transformation to go from the ABC frame to the DQ0 frame. Then you have two types of controller. Okay, the first controller is actually, before I tell you why we have two types of controller, we'll see a little bit how well you know all that. Who can tell in the chat why we have two types of control? The outer control and the inner control. Okay, there is a reason why we have that. Who can tell that quickly in the chat? Okay, I can give you like 5 minutes, the time I finish the explanation. Then I have a look at the chat and see if someone finds the answer. Okay, so the outer control, here we have a loop on the power. So depending of what power strategy you have, you will have different type of power control. So here we selected PQ, so we have a loop on the power, pay reference minus pay measured, then the pi controller, and on the reactive power, Q reference, Q measured, the pi controller, sorry, and all that goes and creates the IQ reference. Okay, if we had selected another mode, here we have the control for the VDC, the DC voltage. Okay, but here in that case it's not selected. And same thing here for the voltage reference. But again, it's not selected here. So this loop determines the the current, the DQ0 reference. The second loop, the inner control loop. Okay, we do the exact same thing with the current, and we find the VD-VQ reference. Okay, so let's see if I had some answer on why we when we have two steps like that. Okay. Okay, so a lot of answer, but I don't think I found a good one. So why is that? It's because if you put an equation of all that, okay, you have a non-linear system where in the same equation you have the voltage, the square of the voltage. So it's too hard to do a control for that. So what we do is we do the control in two steps. Okay, and so like that you can you'd have only linear system, one for the current reference and then for the voltage reference. So that's the reason. It's because first when we put equation of everything, we have a non-linear system. Okay, so in the end here we have the DQ reference. We go back in ABC frame, and it's directly what goes to control the gate, okay, of the IGBTs. We also have here the strategy in case we are islanded. Okay, and you see the input control mode select which one we want. So we'll go into that later. Okay, so it's just a quick overview of the control. Of course, you can modify that. If you want to try a new control, you can modify that. If you want to implement something new, all that can be modified, no problem. That's the beauty of it, actually. Okay, so let's move on and see now what happened when we are in islanding detection. Okay, so other question for you, this one easy, just to see if your chat button works. What variation of voltage and frequency do we expect when I will open this switch? Okay, tell me quickly in the chat. I actually gave the answer before, but it's just to see if your chat button is working. Okay, so I open now that at 0.5 seconds. Okay, and I run this simulation. Okay, so let's see if I have some answer here. Okay, yes, someone find the answer. Of course, it was easy. Okay, it's just nothing will happen because here we are in the worst condition possible. No power is from the grid, and the natural frequency of the natural frequency of the RLC load is 60 Hz. So we expect nothing to happen. So let's verify. So see, it's true. Nothing move actually. We barely see a difference. Okay, I'm not even sure I run the simulation now. Let's do it again to be sure. Well, it's good, so it's normal, nothing move. I'm sure though if we zoom a little bit, we should see something. See, yeah, we see something, but it's so little. So here we get islanded, and almost nothing happened. Same thing probably in the reactive power loop. Okay, you see almost nothing happened. It's like really nothing compared to it. Not even like 0.01%. So we expect that. Okay, so other question for you. So that's, we'll agree to say that it's not a very realistic case because like what's the chance to have such a load? So let's try to see a more realistic case that can occur in a microgrid for nowadays. First, because it's very uncommon a microgrid where the DG produce enough power to match the load. Okay, and here it has to match perfectly. So look, let's play a little bit with the load and see the difference. For example, I have another question for you. What is going to happen if now I change the value of resistance here and I put 50 ohm? Okay, where is it going? Is the voltage going to change? If it change, how? Is the frequency going to change? If it change, how? So let me know. You have like 2 or 3 minutes the time I run the simulation. Let me know what do you think will happen. Okay, I run the simulation. Okay, let me check first in the chat if someone found the answer. Okay, not really. So let's see what's gonna happen. Okay, let me unzoom. So here I just changed the type of load. As you see, the frequency doesn't move much. Okay, the only thing that moves is the power and the voltage drop. Well, yes, it's very characteristic. If you change the resistance, nothing will change for the frequency. You can actually do some end calculation and you will find this answer. Okay, so the power, the voltage change, but the frequency doesn't change. Actually, the voltage drop, the frequency doesn't change. Why does the power here like that is limited? Well, that's for another reason. The reason for that is that in my inverter, okay, I have here a section which is IDQ reference limiter. And I have some limit here in the current and in the current in here. And since the voltage drop, to ensure the same amount of power, I have to inject more current. And in that case, I reach the limit, so I cannot inject enough current. So that's why actually the power of the inverter drop. Okay, so it's interesting. So let's do the same thing. So I put back the other, I put back the old value of resistance. And this time I change the inductance. And instead of putting this, I put 130. Okay, so this time what do we expect? Okay, it's easy. Okay, so this time the voltage doesn't change much, but the frequency drop. Okay, it's logic, but it's good that EMTP can verify that. Okay, so that's good. So now let's play a little bit with the inverter model. So far we have an average value model of inverter. Okay, and let's see what could happen actually let's see what could happen if we go to a detailed model. Okay, so for that, let me remove the capacitance, because such a big value of capacitance will remove all harmonics. Okay, so it's not very representative. We'll see, like, we'll have a super clean signal if we keep this big value and capacitance. Let's keep a RL load, which is in the end more realistic. And to respect a little bit the power flow, I have to change this value of inductance. Okay, so I run the load flow here. Okay, so you see now some reactive power is coming from the grid. And I will add some tool to study harmonics. Okay, so what tool do we use for harmonic study? Well, actually not for harmonic study, for power quality. So one thing that is interesting to look at is the THD. Okay, so you can find that in the library transformation. You have a THD meter. Is it in the library transformation? I don't remember now. Oh yeah, here, harmonic THD. Okay, so I can connect that. So in this, in the mask, you only enter the frequency. So let's code that. Okay, also let's have a look at the current through this switch. Okay, as you know, maybe for the one of you that work with some wind park manufacturer, often they give you all the harmonic content of the current. So that's the one we will find here. In that case, what you do is you replace the DG by a current source, but it's not what we do here. Oh, I have to enable the time domain simulation to have access to the scope. Okay, so let's look at the current. And also, okay, where we'll find the big difference is, let's look at the voltage here, okay, right after the inverter. Right now we use an average value model. So what is it, an average value model? Is that we use ideal voltage source to follow the voltage reference determined by the control. Whereas in detailed value of inverter, as we will see after, we compare this voltage reference with PWM, a triangle, and we'll generate like that the opening and the closing of the gate of the IGBTs. Okay, so let's put the voltage meter here. I have to unlock this circuit first and call that V converter. Okay, and so this time we will change also the control mode. Okay, so when we are in island mode, we will switch to PQ control to VF control. So how do we do that? Okay, we go to the tab control data, and instead of choosing P control, we select VAC-F control. Okay, and so now when I say OK, oh, sorry, no, never mind, you have to select references from input bundle. Okay, and so now when you say OK, you have a new pin which comes, and from this pin you can input all the different references. Okay, so let's do that. So the first one, you see the control mode. So what is it, the control mode? You can, if you input 1 here, it's PQ. If you put 4, it's VF. So what we'll do, it's at 0.5 seconds, we'll switch from 1 to 4. Okay, so how do we do that? Let's take here in the library control the function of U. And in this function, actually, you can write your own mathematical equation, and you can use the time for that. So what will we say? It's like it's 1 plus 3 multiplied by time bigger than 0.5. Okay, so here this condition t larger than 0.5 is 0 when it's true, when it's not true, 1 when it is. So in the end it's 1 plus either 0 or 3. No, so 1 or 4. So we are good here. Okay, I don't actually need an input for that in that case. Then we put the reference for each value. When control mode will be 1, okay, P and Q will be used. When it's 4, it will be V and F. But let's put the reference for all of them. Okay, so the frequency 16. Then VAC. So VAC has to be in peak value phase to ground. Okay, so it's 13.8 multiplied by 1000 multiplied by SQRT 2 divided by 3. Okay, phase to ground and peak value. Then the Q reference is still 0. Well, actually we can say 0 here, the same. The power reference, it's my 2.5 exponent 6, but remember it's a negative number because it's AC to DC. Okay, and here it's when we are in control mode 1, we can select if we control Q, the reactive power, or the voltage. So so far we were controlling the voltage in that the reactive power in that mode, so we put 1. Okay, so we are good to go. Let's simulate that. Actually, let's lower the time step to 10 microseconds. Okay, because after we want to compare with the detailed value model, and the detailed value model requires a small time step. Okay, so let's simulate that and look at the scope. Okay, so I have here the power. So you see now where we are actually. Okay, now all the simulation finished. When we are in islanding mode, as you see now, the voltage here remain at 1 PU, and the frequency as well remain 260 Hz. So because as soon as we get islanded, we change the mode, and we go from PQ to VF. So the DG is not the slack, and it does everything it can. It produces the amount of power necessary to maintain the voltage and the frequency. And so you see that the reactive power generation increases a lot, and the real power remains kind of the same. I mean, it's normal because look at the load flow. In the load flow, the grid didn't produce any power, but it was producing some reactive power. So in the end, here we feel this mismatch, and you see 3.5. So it's pretty interesting. So let's save all those curves and compare with the detail value now. Okay, so to save them, I select them and I click on the small camera. So now you see they are saved. And I change the type of inverter, and I will use the full detail. Remember that we don't have any filter here. I put very big values so to disable it. So we expect a lot of harmonics. Okay, so let's run the same simulation and look at the exact same parameters. Oh, sorry. Okay, so it's interesting. As you see, there's not a big difference actually. The control time, the time response is the same. Okay, here we see a little bit of difference because the voltage, instantaneous voltage, is different. So I mean, it's just a transient response, but really the time response is the same. So it's good. It validates the average value model for stability studies. Now let's have a look at the voltage. Okay, if we look at the voltage, if we zoom, okay, so it has the same shade, the same envelope. However, if we zoom now, we see that superimposed we have the high frequency harmonics. Put them all together and zoom. Okay, you see it's very clear here. Same thing actually if we look at the current in the switch, we will see those same harmonic. Okay, so let me zoom on the current. You see it's the same harmonic. So another thing that could be interesting, and actually that's what we do for power quality, is we monitor the THD. Okay, so let's look at the THD. Here also, it's very interesting. So you see before the islanding, we have a THD of 2.5%, which is already a bit high, but it's okay. However, after the islanded, it grows to 4.3, which is now a lot. Okay, and it's actually everything it's about it's all it's about in microgrid. The problem is that when all the power is generated by inverters, okay, the power quality decreases, of course. That's what we can see here. Here we lose the grid. So all the power is generated with through the inverter, and the grid doesn't doesn't sustain a good quality of power in the voltage. So we can see that here. Okay, so it's pretty interesting. We can also see clearly the harmonics there. Okay, so last thing we can do for power quality is actually check out the frequency in this voltage. So for that we can use a scope view and use this part here, function. So you can select the category harmonic analysis and use the function discrete Fourier. Okay, so if you, let's do that for the voltage of the DG. Okay, I can put that on page 4, for example. Okay, so you can see now all the different frequencies. So the 2000, okay, frequency of the inverter and the multiple of that. So that's the FFT. So we monitor all the frequencies. Another thing you can do is to scope only certain frequency, the one you want. Okay, and in that case you have like some bars that shows the level of each frequency, and you can compare that with the IEEE standard for power frequency. Okay, so yeah, it's pretty interesting. Yeah, so actually something else we can have a look at, and we haven't yet, I forgot to plot it, it's the voltage at the output of the converter. Yeah, I didn't plot it yet. Okay, and so see here we really see like the pulse modulation from the PWM in the voltage, and we don't have the waveform from the ideal voltage source, so that's extremely realistic. Okay, so I think we are good with that. So let's move on with the next. Okay, so what the detection we'll see here is based on the negative sequence injection. So what do is that we inject a little bit of negative sequence in the network. Okay, and so we monitor the variation of the voltage. In the end, if we inject a current, okay, which is a constant current, and we monitor the variation of the voltage, it's like if in the end we measure the negative sequence impedance. And if we lose the grid, then the negative sequence impedance change, and then we can see that. So the advantage of this method, which is an active method, is that even if we are in very islanding detection condition, so no power from the grid, we can still detect that. The disadvantage of that is a part of the capacity of your PV is to inject a second harmonic level of about a second harmonic current of about 5%, and also by you kind of like disturb the signal. You kind of disturb the power quality here by injecting this second harmonic. But it's a very small level, only 5%. And again, in grid connected configuration, the voltage is very good. But when you lose the grid, then you can see that in the voltage. Okay, so let's look at that. So actually, I run the load flow of this simulation already. And I can look at that in scope view. Let me get rid of all this signal. Okay, so let's look at the negative sequence voltage. Okay, so it's very clear here. We see it before and after. So it's very clear here that we have an islanding detection. So it's an interesting method for islanding detection. You can use, so there's this one. Another method would be to try to change a little bit the frequency. When the grid is connected, it's impossible. When the grid is disconnected, it becomes possible. You have a lot of other methods. You can try to change the angle of the voltage, the magnitude. So there's different ways. This is one of them. The interesting part is how do you implement that in emtp? Well, very easy. Okay, here we have a PV. So the PV uses the same type of converter as the one I was showing before. So if I go inside the mask of the PV, okay, you recognize that. And if I go in the grid control, okay, here the subcircuits are a little bit different, but we find the same thing. We have the outer control, the outer loop, and the inner loop. This time in parallel, I put another inner loop, which is for the negative sequence. Okay, and as you see, the reference here is 5% for the D and Q. The D and Q negative sequence current. Okay, the reference is 5%, and we have a loop here. Okay, to inject this current in the grid all the time. So what do we have to do? So we have to use, we have first to calculate the negative sequence DQ0 component. It's actually very easy to do. Okay, if we go in the ABC to DQ0 calculation, we use the same function as usual, but instead of inputted omega t, we input minus omega t. Okay, and in that case, we find the negative sequence DQ0 component. Of course, then we have to filter the second harmonic. Okay, we inject some second harmonic in the current, but for the loop, this second harmonic is not convenient for the DQ0 transformation. So we remove it from the signal, especially for the positive sequence loop. Okay, and so the control loop here is the same thing, except that again, anytime you have omega in a regular loop, here you have minus omega because it's a negative sequence. So it's the case here, you see minus theta grid. So it's the same thing in the end, it's the same loop in parallel. How did I build that? I just copy and pasted it. I modified it myself. And in the end, it generates a voltage reference only for the negative sequence. And this voltage reference is added to the positive sequence loop to create the real voltage reference. Okay, so it's an interesting way of seeing that. It's a method. Okay, so let's go to more interesting stuff now. Okay, so I show you the base. Now I will show you some more realistic grid. Okay, so let me close all these examples. And open the next one. So the next one, it's yes, this one. So here we have a full grid. Okay, it will take some time to open because it's a bit big, but what do we have in this grid? We'll have some batteries, we'll have some photovoltaic plants. Oh, here we go. Okay, so we have here some battery, we have two battery, we have a wind park, we have a solar park, you have some load, so some industrial load, some residential load, and finally here you have some diesel unit in case. Okay, for the first simulation, they are not connected. For the one of you that are emtp user, you will notice that now you can like copy and paste drawing on the symbol of the device. Okay, when you go to edit symbol, you can now copy and paste an image like that. So that's pretty cool. Okay, it's just a drawing. You know, when we talk about smart grid, there has to be nice pictures. That's what it is, smart grid. But now actually we go to a higher level than only the picture. Okay, so in that case, it's very important to have a load flow because we have a lot of different power source. So it's very hard to initialize that in time domain. It will take a lot of time and maybe it will start diverging. So here, very convenient. We have all our sources that are initialized in the load flow. Actually, I run the load flow already, and you can check out the power through every devices. Okay, so the real power, and you can also see the voltage at every node. One thing here, the residential load are unbalanced. Okay, remember I told you that the DQ0 control is challenged by the unbalance. So here it's unbalanced, but it's not a big deal. Okay, you see the voltage here is slightly unbalanced. In EMTP, we can solve the load flow for unbalanced condition, not a problem. We have here a PMU. Okay, so the PMU, it's actually something that we take from the relay library that will be released next month. Okay, so I won't have time to go into the PMU today, but we'll do another webinar on PMU. And here we have the islanding detection logic. Okay, so let me go through first the battery model. Okay, so in the battery model, it's something that you have in your library. You can select what kind of battery you want. Okay, for example, lithium-ion. Then you enter some typical data, the battery voltage, the resistance, the initial state of charge. the nominal capacity of the battery, okay, in megawatt hour of in ampere hour, and the minimum state of charge. Then you have some more advanced parameters. Then the voltage regulation. So as you see, the battery inside the model has a DC-DC converter. Okay, so here you have all the parameters for the DC-DC converter. Okay, so let me now go into the islanding detection. So this PMU here, we have a VT, and in this PMU, if you look at the signal that are sent by the PMU, you have the frequency, the voltage, the rate of change of the frequency, and also inside we put some function like rock off. Okay, I can actually open the mask. Some function like the rate of change of the frequency, the over frequency, under frequency, all that is here. So we selected all this function, and we will use this function to detect islanding as a passive method. Okay, and all that goes inside my islanding detection. And you can see now I have a small strategy. Anytime I have one of these signals, I detect islanding. So here it's your choice. You can add some delay, because you know here it's easy. I do a scenario, I will see a frequency change, and I detect islanding. However, you have other type of study to do. You have, for example, to do a fault and remove the fault and make sure that there is no islanding detecting for that. So you have to simulate like that a lot of different events to see if you detect islanding only in case of islanding and not in case of fault or load shedding or stuff like that. So that's where emtp can become very useful. Okay, here I will show you only how to detect islanding, but you have to do all kind of scenarios that you can think about. Okay, so when islanding is detected, you see here you have the battery supervisor. And if I go inside, okay, it's very simple. If you go inside, you see that when islanding is detected, we go from the control mode 1, which is PQ, to the control mode 4, okay, which is voltage and frequency. Okay, what else in this? Here also in the battery supervisor, we could add a loop for the state of charge of the battery. Okay, for example, if the state of charge is too low, then we ask the inverter to stop producing. So you are completely free to do all those kind of things. Okay, so let's have a look at the result of that. I run the case already because look, it's already 12. I'm supposed to finish soon. So to run a case like that, it will take maybe 3 or 4 minutes. Okay, not even actually, 1 or 2 minutes. So it's pretty fast, and I run 7 seconds of simulation. So it's, believe me, it's actually very fast. Okay, you don't trust me? Let's run it. Okay, let's run it and let's look at the power, the voltage, the frequency, and the islanding detection. Okay, we can actually, like that, display the result while the simulation is going on. Okay, so what happened here? At 0.5, we get islanded. Okay, so as you see, before we are in a steady state. At 0.5, we get islanded. Okay, so we see here that's the positive sequence voltage of the grid goes down. The frequency goes down pretty quickly, actually. And so finally, we detect islanded and the battery change mode. And what is that? Oh, that's the power. You don't need to see that for now. So the battery change mode, and we go back to a normal frequency and a normal voltage. One interesting thing here, look at the frequency. Okay, we can clearly see that before we are landed, we have a very good frequency. After that, we can see the second harmonic because we lose the grid, which is strong, and now we have a microgrid, which is a little bit weaker. So now the frequency, we can see the second harmonic in it. Same thing if we look at the voltage. Okay, but it's still not bad, I mean, those variations. Let's now look at the power generated by everyone. Okay, so the power generated by each battery and the power generated by the PV and the PQ. Okay, so I can superimpose the power from the battery, I can superimpose the power of the the reactive power of the battery. Same thing for the parks. Okay, I'm sorry, it's already 12. I guess we were supposed to do that in 1 hour. If you have other commitments, don't worry, we'll put the video on YouTube and you'll be able to see the end of this webinar. I have maybe like 10 or 15 more minutes to go and then we'll be done. I apologize for that, but it's kind of the most interesting part of the webinar, so I will try to finish it quickly. Okay, so we see here the power generated by everyone. Okay, so that's the power of the park. And that's here the power and the reactive power of the battery. Okay, one thing that you could find weird here, and you are right if you do. First, both don't produce the same amount of power. So that's not what we want, because one will discharge faster. Also, here even worse. One is producing some reactive power, and one is consuming reactive power. Which means we have like rotated power inside of network. That's not what we want. Why is that? Well, because as soon as we islanded the network, we declared 2 slack. So you have 2 slack on your network. So it's over constrained. So you have some power rotating inside the network. And why do we have that? Well, because remember I talked briefly about here the VF control in islanding mode. In islanding mode, you have to do what is called a droop control. And in that case, the real frequency depends also on the power you want to generate. Okay, so here we have to set M and N to some value. So look, I will put some typical value. And so that all the DGs of the grid will produce almost, okay, the same power and reactive power. It's not true it's everything, but at least they will trend to produce the same. Okay, so let's try and run this simulation again. And we'll see the difference. Is it starting? Yeah. Okay, so before nothing happened, that's the initialization. So let's wait 0.5. So here they don't produce anything, okay? It's 0 here. That's only the initialization, but it's something not realistic. It's the ideal voltage source. Okay, so let's wait 0.5. Okay, here we are landed. Here the voltage change, it's only because the power change, it's only because of the transformer. The inverter doesn't produce anything. Now it does. The islanding got detected, okay, and it does. And so you see now the signal. Well, I hope we will see that. We can actually already see the difference in the reactive power. Before one was positive, one was negative. But as you see now, they converge to the same value. So that's very good, okay? Because now we both produce the same, and we don't have the circulating reactive power anymore. It doesn't match exactly, but it's still way better. Okay, so that's a very important point. The droop control when you have several DGs in the same microgrid. Okay, so another thing actually that happened in this grid, in this network, is that since we are producing with the battery, at 2 seconds we decide to disconnect a load, and we'll see if our microgrid is stable. Okay, so we will disconnect one of the load at 2 seconds. So now, so you see the power drop from the battery, so that's good. Okay, and actually now the battery are getting back some power. So that's very good. So now they are charging. If we look at the state of charge of the battery, okay, so of course it's a short simulation, so it hasn't moved very fast, but we can zoom, and you see first it goes down, now it goes up. So we can manage like that the power of the battery. Okay, so really, you can do whatever you want. It's just a question of your imagination, and if you take time to build the strategy with you have the end-door like you see in here. You have some OR, end-door, some timers, some delays, so you can do everything you want. Okay. Okay, so now let's go quickly to the next example. Okay, I had other stuff. I wanted to run the same case with some synchronous machine, but we don't have time. So we go directly to the case where actually the synchronous machine are here in that case as well, where you have several PMU. Okay, that's as well a concern for microgrid. It's like when you have several PMU, how can you manage all the information from the PMU? It's a chance to have all of them, okay? Get redundancy, and so then you can, like that, have a better feedback. Okay, so here what we do, we have the PMU. I improved a little bit their model, and I synchronized them with the GPS. Okay, we have a satellite here that gives the time, and the satellite synchronize all PMU. And so now, so again, I modified a little bit the PMU. Now the information they give to the islanding detection are those one. The rate of change of the frequency, the voltage magnitude and angle, the frequency, the positive negative sequence, and the time. Okay, and so that's important. Now we have the time. And they send like that these threads of signal. We had to the islanding detection, so we had some extra delays. So for one of them, we put a delay of 5 milliseconds, for the other one of 2 milliseconds, and we actually add some noise as well. Okay, so some white noise. So it's really realistic now. You know, it's very nice to do demonstration like that. It's very realistic case. So let's see now the islanding detection. So what do we do? Okay, here, anytime we receive a new thread, we synchronize it. If the time of the two threads doesn't correspond, which would mean that one thread didn't arrive for some reason, we don't consider it. And so we wait that the time of both are the same to take them into account. And you see, then we do a sample of them. Okay, so then we take an average value of both, and we look at the frequency deviation here with a small delay, and then here the rate of change, of the frequency, and we actually do an average on one period. Okay, and we add the delay again. So here what we do is the PMU, the synchrophaser are refreshed. I think it's twice a cycle. Okay, so let's look at the result of this simulation. Okay, sorry, we don't really have time to spend on the case now because it's late, but let's do it quickly. Okay, so if I look at here, what would be interesting is where is it? Islanding detection. Okay, here we have the rate of change, the average actually. Okay, so as you see, the rate of change, it's pretty noisy. Of course, we added noise. And we take the average of these two signals. So you see in green, we have the average. So let's zoom a little bit. Okay, so you see clearly the noise. Okay, the time step here, it's like 150 microseconds. So that's the noise at 50 microseconds. And you see in green the average. So it's very clean. We have a signal that is more clean, and we can take better decision on the green signal compared to the other two, especially when we're talking about rate of change of frequency. Okay, and so that's why we do an averaging here on two cycles. No, on one cycle, sorry. Okay, so here we have the rate of change, same thing for the frequency, and that's how this time we determine the islanding detection. Okay, so quickly let's have a look at the frequency in that case. I mean, there is nothing new, okay, but okay, so you see again when we get islanding. In that case, I don't actually switch the battery. Okay, we just run forever, so you see the voltage change a little bit. We have, however, the synchronous machine, so that's why it doesn't go crazy. That was actually the whole point of this simulation. Maybe I should have explained that, but here we have synchronous machine. We have synchronous machine. The problem with the synchronous machine is that when we get islanded, because of their inertia, the frequency doesn't change much. Okay, and so here that's exactly what happened. You see we get islanded, the frequency doesn't change very fast. But still we detect, but again in that case, I don't switch the mode of the battery. I should, but I didn't, okay, because I wanted to see what happened if I don't. Okay, so that was an interesting thing. Last part now, okay, which is more for fun, but I think it's very interesting for a lot of you. It's the black start. Okay, and I have approximately 5 minutes to talk about the black start. It's too bad because I would love to talk about it for an hour, but we have 5 minutes. Okay, so in that case, what happened? Everything, okay, is shut down. Let's say we are the day after Katrina. Everything is shut down. As you see, the grid is off because it's completely shut down as well. But since we have DGs, we want to start our grid and operate without the main grid. So we have no ideal source here. So what do we do? Okay, first the loads are disconnected. So what do? We'll use the battery to first energize this part of the grid. Then we will start those diesel generator. Okay, so slowly the voltage will ramp here, and then synchronize them with the rest of the network. Okay, and we will ask them to produce some power. While they produce some power, we will actually store the power in the battery. Finally, when the synchronous machine will reach the steady state, we will reconnect the residential load, okay, and then the network will be ready to go. Cool, eh? So let's look at those. Okay, so let me remove the plot before and look at the result. So I click on View with View. I run this simulation already because, again, we have no time. Okay, so first let's start with the voltage, okay, at the terminal of the battery. So if I go to the node voltage, it's here, here. Okay, let's only look at the voltage on phase A. Okay, so initially, nothing. Okay, we are at 0, then we start, and then we are energized. We can have a quick look at the power generated by those batteries. When that happened. Okay, so at the beginning, I have to zoom, sorry. Yes, this simulation lasts 1 minute, so it's pretty long. At the beginning, I have 0. If I zoom as well as that. I'm struggling. Okay, you have 0, then at point 1, I'll energize, and then I reach the steady state. We produce very little power, actually almost no power at all, only reactive power. Of course, why? Here the battery are only used for VAR compensation. We have no load, we have only the lines, so the battery are only here to inject the VAR compensation, to inject VAR, to maintain the voltage, and the loss from the lines. We have also for VAR compensation in the library, if you go to advanced, you have some StatCom, okay, or SVC, so you can use that as well. It's the same concept. Instead of having a battery here, we have a capacitance. Okay, so then let's look at the machine. The machine, to be able to start them from 0, you have to check the option machine at standstill, okay, which means they don't turn at the beginning. And then slowly, okay, I have a started sequence here. Okay, at like 0.1 second, I start, it's here, sorry, no, where is it? Here, yes. At 0.1 second, I start the diesel. Okay, so that's my startup sequence. See, you have some delays to reconnect the load, etc. So yeah, that's your strategy. Okay, so I start the battery, I start the machines. So let's look at the voltage now of the machine and the voltage of the system. Again, only on phase A. So that, I did something, so that we can see the synchronization. Okay, so you see that we start from 0. Initially we are at 0, then slowly the machine starts rotating, so that means the governor starts injecting mechanical power, and the field voltage also starts maintaining the voltage. So slowly we ramp, okay, then we start reaching the steady state. At that point, we synchronized. Okay, if we put both of them together, okay, we can see that at a certain point here, we synchronize them and they are the same. Okay, here the stability of the machine can be discussed. Okay, it's actually an old governor and AVR. I'm sure it's possible to find a better one, but it's okay. The goal is not to discuss the control of the machine. Here we have one. It could be improved. Okay, let's quickly have a look at the synchronizer. Okay, what do we do here? Well, we check out the condition on both sides of the breaker. Here the RMS voltage, and when the RMS voltage, the absolute value, is under a certain threshold, we give the authorization for that. Same thing for the frequency, and same thing for the angle of the voltage. When we have the three conditions, we ask the breaker to close, with a small delay actually. Okay, and so for the AVR, well, the AVR, I mean, we won't have time to go in detail for the AVR again, unfortunately, but you have here an exciter, here you have the governor, okay, and so they are built like that with transfer function. All that you can modify it, so you have the transfer function for each part of the engine. All that you can modify it. We actually have a library of AVR and governor, and if you are looking at one which is not in the library, you can contact us. We have actually some secret library that will be integrated in the new version, probably the next one. Okay, so I think that's what we have to see in this. I think that's what we have to see in there. So yeah, let's quickly have a look at the. I didn't run the simulation for long enough. Okay, it's not a problem. So you see here we connect the synchronous machine, so they start producing. Actually, that's the battery. Let me add the machines. Now it's here. Power diesel, and it's on page 2. Okay, here it is. Okay, so you see the diesel. There are those two here. Okay, so we start ramping the power here, like we said. Okay, and because we produce power and the load are not connected yet, the battery are taking this power. Okay, so you see the battery here that is taking the power. Another thing we can see is probably I didn't enable the droop control in that case. So that's why both batteries, which are here and here, don't accumulate the same power. Okay, and so then we reconnect to the line and we reconnect the load. It's too bad I didn't run the simulation for long enough. It's my fault. But I mean, the most difficult part is really this one, synchronizing the machine. So after, everyone will produce for the load. And our system is islanded but operating. And you can reproduce some fault, load shedding, and see how the network reacts. Because yeah, it can be sometimes a challenge when you have some synchronous machine, okay, that interact with inverters controller, okay, because they don't have the same speed, and we can play a little bit with this case. If we put some different wind park, you will see that you can find some very bad interaction, and you can have some subsynchronous resonance of the microgrid, which is very bad because it can damage a lot all the mechanical parts. Okay, so that's one interesting thing to do, is that if you can have some subsynchronous resonance when you have some events. Okay, you can see them pretty fast. You can do a fault, for example, and clear the fault, and you can see after if you have some subsynchronous resonance or how the whole grid reacts. Okay, but it's still like it's still very good, all that. Okay, so I didn't quite use a lot this presentation, but anyway, there was not much in there. So for the islanding detection, okay, here some few other methods. I talked about them. Two other one actually are like, okay, you can use communication. You can also use something which shows line carrier communication. Okay, which means that you will use the line to find the load flow. So you have you inject from the utility side, you inject some high frequency signal, and you have some receptor on the microgrid side, and if at a point you lose them, you declare the islanding. You can simulate all that with the MTP actually. As you know, we have some very advanced model of line that are frequency dependent and which reproduce the propagation of the waveform. Okay, so you can completely study that. It's not a problem, and we will probably do a webinar on that as well eventually. Okay, so to conclude, first we show that EMTP is a very flexible environment for any kind of power study. Okay, so as you see, in few clicks, we can modify the network, remove a load, add a new load. We run the load flow and the time domain, and everything is initialized. We don't have to change anything or change environment. That's a pretty unique, actually, feature. So you can use it to verify the controller parameters, okay, and the stability of the network. To identify, like I said, some subsynchronous oscillation or bad interaction between the AVR and the governor of the synchronous machine on one side and the inverter control on the other side. You can study power quality and also black start. Then, of course, as you know, transient software like emtp are used for other purposes like insolation coordination, TRV, ferroresonance, protection, okay, and all that is actually also important in case of microgrid. Okay, so for the future webinar, for the next months, we will do a webinar with Bombardier on DC power system analysis in rail passenger vehicle using EMTP. So I really recommend you to have a look at this webinar. It's pretty interesting. They get in a very detailed model for the train and the station. They use a lot of power electronics, DC system. They do fault in the DC system. They model the breakers for the DC system. So it will be very interesting. You can actually register now if you go to emtp-software.com in webinar. Then the months after, we present the new protective relay library, also very interesting. However, in that case, I will do it. Okay, sorry, you might be bored with me, but it will be me again. And you have available all the previous webinar on YouTube. Okay, you just have to open YouTube, search for EMTP, you will find it, and we'll post this webinar in the following days. We'll put this webinar that we recorded today. Okay, so last thing, this one is the last one. So after this webinar, if you're interested in trying EMTP or having a quotation, please contact us. Okay, you have the address here. Also, we have special arrangement for universities, so contact us as well, and we can provide you some license for your research and education. Also, finally, remember that for all type of engineering services, for smart grid, but also for more classic study like insolation, coordination, TRV, power quality, etc., we offer engineering services. So if you are interested by that, it's the same address, contact us, and we'll be happy to help you with your study and send you a quote to do the study for you. Okay, so thank you very much. I really hope you enjoyed this webinar. Please take some time to fill out the feedback so that we can improve, and you can also suggest suggest some subject for future webinar. And again, I apologize for the length. I got too much into it, but it's better more than not enough. Too much than not enough. Okay, so thank you very much. We stay connected for the next 15 minutes. If you have any question, we will answer them. Don't hesitate. And else, I hope to see you soon. Bye-bye.